Hello, my name is Jessica, and I'm here to present the Group 9 Machine Learning presentation. Our project is titled Lesion Vision, and we focus on skin lesion detection and identification. Now, I'll let the rest of my group introduce themselves.
Hi, my name is Jonathan. I'm a cognitive science computation focus, and I will also like to introduce Victor, a computer science major.
Hi, my name's Naomi. I'm an applied mathematics major.
Hi, my name's Richard. I'm a statistics major.
Speaking in place for his absence is Primo, a computer science major.
I am Tanaya. I'm a computer science major.
And for the user interface and data visualizations team, I'm Kevin, and I'm a computer science major.
And my name is Bin, and I'm also a computer science major.
Hello, everyone. My name is Jianbin. My major is computer science.
Hello, I'm Matt. I'm a computer science major, and I worked on the machine learning component.
I'm Scott. I also worked on machine learning, and I'm computer science and engineering.
Again, my name is Jessica, and I'm a computer science major, and I'm the group leader.
So the problem that our team is addressing is skin cancer. It's the most common type of cancer found worldwide and in the US. 1 in every 5 Americans are expected to develop skin cancer by the time they reach 70, and as of 2021, a total of 5.4 million non-melanoma skin cancers have been diagnosed, affecting over 3.3 million Americans. This year, over 100,000 cases of melanoma are expected to be diagnosed in the US. It is estimated that over 7,000 people will die from melanoma. Research has shown that treatment is most effective the sooner the cancer is caught. Over 99% of patients who have had skin cancer detected early have survived. But with 10% of Americans being without health insurance, a visit to the dermatologist is costly, so many individuals aren't always able to catch the cancer early.
Our proposed solution is to empower these individuals by giving them a dermatologist-level classification of skin cancer by utilizing deep neural networks. Instead of going through the typical process of an initial clinical screening and many follow-up analyses by dermatologists, users can just input an image of their skin lesion into a trained model for easy classification. The perfect way to tackle this problem is to use a convolutional neural network for identifying the fine-grained variability of skin lesions. Our convolutional neural network, trained on thousands of images of different categories of skin lesions, both malignant and benign, can help give users a convenient diagnosis without having to consult a dermatologist.
So just a quick overview of the data set that we're using. It is the humans against machine with a 10,000 training images data set. It includes exactly 10,015 images of skin lesions along with their respective metadata. While most of the features in this table are self-explanatory, such as some used for identification purposes and some for describing the patient with a skin lesion, I will clarify the meaning of DX and DX type. So DX is the diagnosis of each skin lesion in our data set. There are 7 unique values for this attribute. And DX type is the column which is basically abbreviated for diagnosis type. This is just to describe which medical method was used to verify the skin labels. And I'll go ahead and let John talk about the limitations and underlying biases of our data set.
I'll be talking about our literature review and their shortcomings. The dataset that we will be using to train our model is the HAM 10,000 dataset, a multi-source collection of images that have been collected over a period of 20 years. Though it is multi-source, all images have been digitally processed and cropped so that they are uniform and capture the skin lesion in its entirety. Skin lesion diagnoses have been confirmed through histopathology, confocal expert consensus, and follow-up, so there are valid ground truths verifying our skin lesion labels. Even though the dataset contains only 7 kinds of skin lesion labels, this still encompasses over 95% of the examined skin lesions from 2 study sites from the data. The key takeaway is that our data has been highly scrutinized, reviewed, and processed, meaning the data we'll be using to train our model was taken under ideal conditions, which won't be the case for predicting on new data. Here is a visual diagram on which the data was collected and processed. The images were first taken and stored in a database along with metadata from multiple clinics. Then, they were confirmed through different ground truth methods as explained from previous slides. Finally, they were standardized to a particular image format that we can use to train a model.
By studying previous research on training a model to classify skin lesions, It has given us insights into how we should approach the construction and training of our model, as well as understanding its limitations in making accurate predictions. Now, as we know, neural networks are not scale and rotational invariant, meaning that our model would have difficulties predicting skin lesions that are outside of our dataset. For example, a photo taken by your phone is vastly different than a photo taken professionally at a clinic and processed carefully for uniformity. An example that will lower our model accuracy is shown on the right, where the skin lesion on the left is not centered and smaller compared to the one on the right, which was taken from the human against machine 10,000 dataset and was processed to be as clear as possible. Another drawback is that a convolutional neural network is slow to train. Our model took over an hour to train, so updating a model on new data would inevitably be slow and potentially costly. Lastly, we also know that convolutional neural networks are vulnerable to adversarial attacks. For example, an adversary can add noise to an image and it can completely distort and change the prediction outcome. Now we will move on to our exploratory data analysis.
By far, the most common skin lesions in this dataset are melanocytic nevi, so in other words, moles. These lesions make up approximately 90% of the data in most age groups, but there are some exceptions. Benign keratosis-like lesions and vascular lesions can come up regularly in the 0 age group, and benign keratosis-like lesions, melanomas, and eventually basal cell carcinomas start to overtake nevi for ages after 45. But benign lesions are still very common for most demographics. The ages 40 to 55 are the most represented in this data, as this plot shows here, so they seem to be the most prone to skin disease in general. Although, however, our model might be biased towards these groups. In terms of gender differences, women are slightly more likely to have melanocytic nevi, vascular lesions, and dermatofibromas, while male patients are slightly more likely to have benign keratosis-like lesions, melanomas, basal cell carcinomas, and actinic keratoses or intraepithelial carcinomas. Overall, this EDA showed that there was a little potential for predicting tumor types based on demographic data alone, but effective predictions should still rely on the images themselves. Furthermore, this shows that the dataset is not already balanced, which is probably related to how rare certain lesions are. So some resampling might be necessary before training our model.
In preparing our data to be fed into our neural network, we first had to convert every single image to RGB pixel data values and scale it down to 32 by 32 pixel images. This made it so that the training time for the model wouldn't take too long. We then one-hot encoded our skin disease labels, which we decided would be better for training compared to label encoding, because in that way we would not run the risk of the model imposing any ordinality in the labels. We also normalized the RGB pixel values from 0 to 255 down to 0 to 1. This further helps with the training of the model.
Okay, in part 2, from our EDA, we saw that velocity nevi make up a very large portion of our data set, while other skin lesions only have counts of a few hundreds out of a data set of 10,000 samples. To address this problem, we first oversample from minority classes as well as undersample from the majority class. We then took our images and applied data augmentation so that the neural network could train on skin lesions at different orientations and in different positions. After, our data was completely ready to be trained on.
So how does our model start from an image of a skin lesion, evaluate it, and then classify it as its correct type? Well, this is from the inner workings of multiple different kinds of layers that process and update the weights in our neural network. We have to first start with the convolutional layer. Our neural network receives the data of our image as a 4-dimensional array of values. And you might be asking, why does our image data have 4 dimensions? Well, to break it down, we have the number of samples, columns, rows, and color channels. We specify a kernel size for our convolutional layer, which in our case is essentially a 3x3 window, which scans over our images, shifting a specified pixel width at a time. These windows are essentially filters with different weights for each pixel of our kernel. And depending on what kinds of weights that you have on your kernel filter, different kinds of features will be extracted. So the output from our convolutional layer is called a feature map. And then our next layer is called the max pooling layer, which then extracts the largest value from its inputted feature map. And then it again maps it to another feature map. So after running a few of these layers, our input vectors could end up having 6 dimensions. So this is why it's important to have a layer that flattens down these features into a single dimensional column, which is able to be connected to a fully dense layer and then mapped to our output layer for its prediction. And when working with deep neural networks, it's good practice to use a batch normalization layer, which normalizes the data and prevents inputs from undergoing a process called covariate shift, which would then destabilize the training of our model. We then also have a dropout layer, which prevents our model from overfitting and normalizes our inputs to each hidden layer. I know that was a lot to take in, but a high model accuracy is nothing without understanding the behavior of the model, which led us to the outcome in the first place. And I'll go ahead and let Victor talk us through the different kinds of technologies that we use to build our project.
We used a variety of technologies and frameworks. For exploratory data analysis, we used Google Colab, and we used Python libraries such as Seaborn, Pandas, and Matplotlib. For data pre-processing and model training, we used scikit-learn, TensorFlow, and Keras. For the front-end portion, we used Streamlit to create a demo of our model. And finally, we used GitHub for version control.
Hi, we are the front-end user interface team, and we'll go over how we made our application and show a quick demo. Firstly, I'd like to introduce Streamlit. Streamlit is the built-in library we use to integrate our back-end machine learning model with a nice-looking user interface. We chose Streamlit because it's built specifically for these machine learning applications, and it makes it very easy to display elements on our webpage.
So now here's a brief overview of our code. First, we imported the data, trained it, imported the trained model, and then got user inputs, and then diagnosed the twin problem, and then displayed different charts in the end.
So let's see our application in action. Say I am a 21-year-old male, and the part I took this picture in was in my face. And here I took a picture on my phone, uploaded it to my laptop, and it's ready to be evaluated by our model here. So now that the user inputs have loaded, we can see this first chart, which shows the kinds of skin problems that you are most likely to have given the inputted age and sex. And then we load our pre-trained model, which will make our web application run much faster. And we can see that our skin problem was diagnosed as Bowen's disease. And here we can see a chart that shows what percentage of skin diseases matches your classification. It looks like we're a minority here with 3.3%. And here is another chart that shows the frequency distribution of gender. You can see that it's predominantly males who have this disease. And this final chart shows the distribution of the skin localizations where it is found. And it looks like face is the most common. So that's a relief. And now we can learn more about our diagnosis by clicking this link. And it will take us to credible information about Bowen's disease.
So now that the user has updated their information, we can see that the previous chart of the likely skin problems you're likely to have, given your age and sex, has been updated. We can also see that the model has again been loaded, and it has diagnosed the problem as melanocytic nevi. And it seems that this disease is occurred in our data set to 66% of the patient. And it seems like male and female have the same frequency of having the disease, and that the lower extremity is most likely body part to have this disease, but the back is the second most, and that's what we had this pigment in. And if we want to learn more about this diagnosis, then we can click here and go to our trusted website and learn more about it.
And that concludes our demo. Thank you.
Thank you.